So we're going to now start talking about moment of inertia. How do I quantify the inertial quantity of rotation, right? The resistance to rotation, to angular acceleration, right? Where we put the pivot point really matters, right? Where we try to pivot an object around really matters. We talked about the last lecture, true lecture, not lecture 2.5, but in lecture 2 we talked about the natural pivot point of an object is the center of mass. But if I try to exert an external pivot point on something, that can really change how easy or how hard it is to accelerate this object angularly, to start to spin it. The image I like to have in my head is a log. Think about a tree trunk, right? Some wood log. If I try to rotate that log, to spin that log just by rolling it along its long axis, that's a lot easier than trying to take one end of the log and flip it end over end on each other, right? And that has to do with the pivot point, right? What axis are we pivoting around? What axis are we rotating around? So how do we quantify that? Right? How do we quantify that? And just to kind of give a brief description or illustration of what I'm talking about a log, and if I rotate it, trying to just rotate it around its kind of center long axis, as opposed to taking the exact same log and trying to now flip it end over end, right, and have this side go this way. So that's and having either the pivot point here or even the pivot point there, right? And that actually does make a difference. That makes actually a huge difference where we decide to put that pivot point. So how do we start to quantify this? Just like with center of mass, we're going to bias this. We're going to weight it. We're going to weight the calculation based on not only the distribution of mass, but how far that mass is from the pivot point, right? So for moment of inertia, we're going to define it as the letter I. Folks, I don't know. I have no idea why is it the letter I. Probably for inertia, but then mass probably would have been, I don't know why. I mean, mass is a general inertia quantity. A moment of inertia. I don't know. It's probably I just for inertia, but it's still confusing. And I know as engineers, if you're taking statics or dynamics, right, you're going to talk about moments more as torques. We're going to call them torques. You're going to call them moments. This is a small translational kind of gap here, failure to communicate, but it still ends up being the same thing. Anyways, I is equal to m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus dot 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 mi ri squared, right? So it's a sum. It's again a sum, and we're breaking it into these really small chunks of m's, right? I can't get away with just saying the big mass m unless I'm doing a full integration and showing it mathematically, right? Rigorously mathematically. So really this turns into the sum over I of mi ri squared. And again, we're not going to use this really general definition unless we're giving you, maybe two or three points and a shared pivot point, and we're saying how does what's the moment of inertia of this very, very simple system. But a continuous system, you're not going to actually do this out. You're especially not going to actually carry out the integration, right, of r squared dm. That's just not something that we're going to do in this class. We could, but we're not going to. All right. So r, by the way, so m is obviously the chunk, right? And r, I think I've said this, but I want to say it again. r is the distance from that chunk of mass to the pivot point. If there's no external pivot point, no forced pivot point, it's going to be the center of mass, right? But if there is a forced pivot point, let's say with a door handle or something like that, right, that pivot point is right here. My mass is going to be somewhere else. Again, this will either be a very simple system they're asking you to solve for, and I think the homework has one or two problems like this. I'll try and throw a worked example into the mix to talk about that. We're not doing a lecture 3.5, but I'll try and throw a quick example of that into the mix. The big thing, again, I want to remind ourselves is that I is this, almost like a rotational mass. It's careful. You gotta be careful talking to people about that and saying, oh, it's a rotational mass. It's an inertial quantity that quantifies the resistance to angular acceleration. Right? That's the kind of snobby way of talking about it, but it's truly, that's the specific definition. I'm generalizing. I'm kind of smearing out some of the details when I say it's a rotational mass. So don't walk into your statics class and say, oh, it's a rotational mass. Okay, so calm down. It's like a rotational mass. It's like a rotational mass. That's where I'm going to stop it. Next time we're going to pick it up with parallel axis theorem, which is a little bit of weird. It sounds weird and it sounds complicated. It's not. I'm going to try and pare it down for you, but we'll pick that up next time. Have a good one. I'll see you later.